Thank you. So yesterday there were a couple of presentations about fighting DDoS, and I guess it's been mentioned a few times today as well. And this is going to be a bit about that as well. So DDoS is a big disruption, and of course there are other forms of disruption as well. Sometimes even misconfigurations can be very disruptive, and when you're protecting your network or your services, it's important to think about how you can take care of all of these problems. I've been running all sorts of services, and especially IRC service is something that back in the 90s got a lot of DDoS. Well, I guess it's still getting a lot of DDoS, but not as much as back then. And also we've got more measures protecting it now than we used to back then. A few vendors have good tools for protecting all the sort of protections that I'm talking here. So I'll also be talking about how, or wishing basically how the vendors could do better. So back in the 90s, I was a Cisco fanboy because like up until 97, 98, there really weren't any other options. But then Juniper came along, and at some point I had to switch to Juniper. And once I got that big change through my brain, I actually fell in love with it because the filters, packet filters, route filters, all sorts of things were a lot more expressive and easier to comprehend than like route maps in Cisco's. And also, well, there's another slide about that. I'll come back to that problem later. But anyway, so I fell in love with Juniper. But now, again, there are lots more vendors out there than there were a few decades ago. And so I'm basically having to change again and finding that a lot of the tools that I like to use on Juniper either don't exist on some other vendors or are not as nice to use, not as easy to use. One of the features in Juniper, for example, that I really liked is that you can build your filters from smaller segments. So, for example, you can have a segment that contains all the necessary protocols and prefix lists and whatever for network management. And you can put that on every interface where you have something you need to manage. And then you can have a second segment that has generic rules for like web services. And you can put that on the interfaces where you have web servers. Then you can have a segment for mail servers and so on. And so basically it's code reuse. And the other thing is that things like prefix lists can be reused in many places. So you can like write one trusted servers or trusted addresses list and then use it in many places, or you can have one golden prefixes for like root name server routes and use that in multiple places or whatever. Yeah. So I'm taking the IRC as an example. There are some pseudocode segments on these slides, but they are exactly that, pseudocode. They look a bit like Juniper filters, but they're not Juniper filters. I first tried to put real Juniper filters here, but they are so verbose that it would have been so small text that even I couldn't read it. So I compressed them into this pseudocode format. So as I said, IRC used to get a lot of DDoS. And IRC as a service is not trivial to defend because it requires a lot of different ports. It requires both incoming and outgoing connections, and they have very different needs. So I'll be going through the different types of packets that we need to take care of. Of course, in IRC's case, not all packets are equally critical. So there are some packets that you need to protect more than others. But this is all applicable to many other things as well. So the first thing is discard everything you don't need. That's usually simple, except in the case of IRC, when there are so many different protocols, and when you first start building the firewall, you don't even remember all the little protocols that you need to take care of. So that is often the biggest thing that you have to find out all the traffic that the server actually needs, and then add an allow rule for or accept rule for all of that, and then finally discard everything else. The second problem that is common to most protocols is that since you can't actually block the production traffic, how do you protect that? And for example, in the case of web services, that is a really difficult thing to do with a router or a simple packet filter, because you don't need a lot of packets to DDoS a CGI script. If you've got a very poorly written CGI script that makes big backend SQL queries or whatever, your service can be brought down with 1,000 web queries a second. And that is so small an amount that the router is not really the right tool there. Some front-end web proxy is probably, or load balancer is a better tool for that particular case. So IRC, for example, is easier to protect in this case, the production ports. Well, using stateful firewalls was suggested back in the 90s. Of course, back then the IRC server ran in a university network in Tampere. And they had just gotten a huge stateful firewall. But the thing about stateful firewalls when you are trying to use them to protect against DDoS is that they do protect your service from DDoS the same way a fuse protects an electrical circuit. So it just blows up. So the next thing that we went for is to limit traffic levels. So basically, you can do this in stages so that at your network edge, you can have huge limits. Then closer to the servers, you can have smaller limits. And then on the server itself, you might have some limits as well. The point is that at each stage, you limit the traffic to something that the next stage can handle. So if your upstream is like a 100 gigabit port, but your server ports are 10 gigabits, then at the upstream level, you need to limit the traffic such that it fits into the next stage links, or doesn't go at least a lot above that. And then at that stage, at the server edge or network server edge, you limit to a level that the server can handle without blowing up. But there's a catch to this, because DDoS often tries to turn your service off. So this is a bit similar to what yesterday's presentation about FastNetMon said about black hole routes, that if you yourself turn your service off, then you are doing the DDoS thing, work for them. So if you make it easier for the attacker to shut down the service by having a limit that is too low, then you are making it easier for the attacker to achieve whatever it is they're trying to achieve. In the case of IRC service, the attacks usually just, they don't try to turn off the IRC service, they try to gain advantage within the IRC chat network, which is usually gained by making the network split into smaller sub-networks and then making state alterations in one of these splinters and then letting it heal up again. So that was the usual attack type and the reason why IRC was attacked, making the network split. So basically, to protect against that, if you can protect your service against what it is that they are trying to achieve without actually bringing down the service, then it'll send a signal to the attackers that attacking is not very fruitful. So basically what we did was we protected the server links separately from the client links. The server links often use the same ports as the client links, so it's not necessarily easy. Basically, in our case, we had the list of IRC servers that we have configured links with, and then we policed that traffic to something that was way above what the server links would ever use. There was actually also a burst because back then the heal burst, as it would be called, was 30 megabytes. So we allowed, the police are allowed the burst automatically before starting to limit traffic. But normal server link traffic was less than a megabit, like a few hundred kilobits. So 10 megabits back then was way more than was necessary for the server links. And then the IRC clients, the rest of the connections, IRC service doesn't use a lot of bandwidth because it's pure text, no pictures or animated videos or whatever. Of course, the second thing that they might want to attack is make it impossible for clients to connect or get all the clients to disconnect. So basically, TCP connections are divided into two stages, or several stages actually. But the first stage, the initial connection setup stage, the so-called SYN flood, is often one of the attack types. So for client connections, we separated the SYN stage and the normal connection stage into separate firewall terms and separate policers, so that if there's an attack against one, it doesn't affect the other. So for example, if there's a SYN flood, new connections are lost in the flood, but existing connections are preserved. And of course, since the server is managed with SSH, then it could also be attacked. So we needed to do something like that for SSH as well, and some other protocols as well. So most of the attackers, script kiddies is a term coined, I believe, in relation to these IRC server attacks. The term script kiddie meant a kid that just went to some website and downloaded a script that did the attack. So they didn't know what they were doing. They just knew that this program would do what they want. So basically, they were using off-the-shelf tools, and they would usually only use one attack mechanism or attack one port or whatever. So when every single thing we accept through the firewall has its separate policer, an attack on one type will only affect that type. So the other traffic will still pass through normally. Like, so as I mentioned on the previous slide, new connections might be disrupted, but existing ones would still be okay. Or SSH management connections couldn't be established, but the server still operates. Or if there are existing SSH connections, then those would be okay, or whatever. Well, as I mentioned, IRC uses a lot of protocols. So when a new client connects to IRC, it is checked for all sorts of abuse, potential abuse features, if I could call them that. And of course, the client is, or the end user is identified if possible. So the server actually probes the client IP address, dozen ports TCP for web proxies, SOX proxies, possibly some other proxies as well. And of course, the ident port is queried. So all of this traffic also needs to be allowed for. But if these checks fail, then usually the client is still let in. It's just put in restricted mode or something, so that they can't, for example, gain privileges on any channel or whatever. So if somebody attacks these probes, probe attempts, generates traffic that would overload the policer for the probe ports, it's not as critical as the normal production ports. Of course, what we could do is we could have separate limits for every port. Then if just one of those ports is attacked, then it doesn't, it's a separate policer and it only affects that check. And of course, here this destination port and source port are swapped because these are outgoing connections. So this filter would be on the router facing toward the server for packets going to the server. So the destination ports are random because the server uses random high ports to initiate these test connections. And then, of course, there are a lot of other important protocols that are needed, like DNS. The service makes a lot of DNS queries all the time. The router in front of the service is made redundant with VRRP, which these days uses IPsec for security. So you need to protect that. And with that in mind, TTL 255 is a good thing to add there, because those packets will always have the maximum TTL and they are link local protocols. So if you ever see a VRRP packet with a smaller TTL, it's a spoof attempt. So you can just drop it. You don't even need to police it. NTP, IRC needs timestamps for logs, just like every other service. And if you need to correlate attacks or whatever using the logs, you really want good timestamps. So you need to allow NTP. In our case, also the servers used to be NTP servers for some other servers. So we needed to allow more than just NTP peers traffics. But the NTP is one of the protocols that is often used as a DDoS amplification service. And but it's easy to, or relatively easy to recognize that, because normal NTP queries and responses are short packets, less than 100 bytes, whereas that reflected traffic is usually hundreds or thousands of bytes. So you can match on packet length in the case of NTP and only allow those short packets through. So you can also get rid of a lot of potential attack traffic that way. And ICMP, you need to let ICMP through, but you don't necessarily need all ICMP. But traceroute is important for debugging, and path MTU discovery is important for the actual service itself. A lot of IRC servers users used to come over like dial-up connections or other slow connections that used shorter MTU. So it's important. So your ICMP, you should have a rate limiter on the ICMP, but you can list all the actual ICMP types that you actually need rather than allowing everything through. And of course, you could limit traceroute ICMP to like 1 megabit or a few hundred kilobits. Path MTU, I think a few hundred kilobits would be quite enough for that as well. And so you could divide it into separate categories if you wanted more protection. But then you can do this on other levels as well. And here is an example of a layer 2 approach on internet exchange points. So a lot of IXPs forbid running internal routing protocols like OSPF or IGRP on the network or many other link local protocols as well. So you could block those. VRRP is another example that is usually not allowed on the IXP shared medium. Now, I'm not advocating that you should block all of BGP at an IXP, but you could block parts of it. So basically, TTL security means that BGP connections as well use TTL 255, so that if a packet with a smaller TTL enters your IXP, then it's a spoof attempt from somewhere further above, further along the field. But of course, this is tricky because there could be also BGP connections going over the shared medium between like RIPE RIS service, and you don't want to block that. So you also need to check that the destination address is actually one of the shared medium IP addresses before you go ahead and try to do anything. So TTL security, I'm not advocating that everyone should do it, but at TREX in Tampere, we are heading that way. All our members have already, to the best of our knowledge, configured TTL security with each other. We know that our own route servers and our own routers require it, and all the sessions are still up. So at least to what us, they've done it. So the next step, we haven't gone that far yet, but the next step is that we could just filter it straight at the switches. So if somebody doesn't, if one of our members don't have the hygiene filters on their routers that would prevent this sort of attack, then the switches themselves will step in and do the filtering. Another BGP filtering type is RFC 8327, which basically means when we are about to do maintenance on the switch, we can block even the remaining BGP sessions on the subnet so that the BGP sessions die and the routes disappear and the traffic goes elsewhere before maintenance. So that is another example of layer 2 filtering at an IXP that could take place. Now, these examples on the right are more hypothetical because we found out, I don't remember exactly, I think it was the destination port that didn't actually exist, at least in that Junos version that we were using at that point. So we would have had to do that using flex matching, but it was basically doable, but not as easily. So maybe even Juniper can still improve, although I don't know, newer software versions probably have this already. You could also rate limit IPv6 link local traffic or detect IPv6 link local traffic that isn't actually link local. If you set up a black hole MAC address at the IXP, then you can, of course, just block that in the same firewall as well. Just make sure that you still allow ARP traffic for it so that it works. So a lot of vendors started out by copying Cisco in either in style or even more closely. And the problem I had with Cisco was that over time they realized that their filtering syntax was limited, and they created new syntax to fix those limitations. And basically they now have like a dozen different AZL types, and it's not really helping anybody. And of course, all the vendors that copied that are in the same situation. A lot of the network operating systems, the new ones, run Linux, and some of them even use a Linux kernel abstractions for some of their own services, like they might be mapping switchboard into Linux kernel interfaces or something like that. So this gave me one approach that could be taken to improve other filters, other vendors' filters. Use something Linux already has. So Linux is switching to NF tables from IP tables. And NF tables basically combines all the old table types into one abstraction, and it allows to combine a filter rule that works for multiple address families. And it's a very powerful language. You can chain all sorts of things in it. But implementing it in merchant silicon, of course, it's going to be pretty difficult. But in my views, it would be a lot better than what Juniper is now. Here's an example of what it might look like. So this is a sort of dual stack filter rule. The first rule just checks input interface name. So it works for both IPv4 and IPv6. Again, this is slightly pseudo-coded. The real filters are a bit longer, but not much. The second and third rules match actual source addresses for first IPv4 and IPv6. So those rules only work for one address family each. And the rest of the rules just find UDP or TCP packets inside the IPv4 or IPv6 and make matches there. Now, I'm not saying that if somebody does want to go this way that they should implement the whole thing in one go, but there are a lot of, well, basically the basic functionality you should go for first, and then maybe expand when you have time, and especially if customers demand certain features. Like static prefix lists are a simple thing you should implement right away, but all the dynamism that NF tables supports for address lists and prefix lists is not necessary to begin with. Maybe later, if you find a neat way of implementing, then why not? Well, that's the core presentation. I do have a couple of backup slides, but let's see if there are any questions first.
No questions? No? No, you're not. Yeah.
Well, I'll use this backup slide to fill some time. So basically, one of the technical issues with some switch platforms is that they only support lookups before filter rules, and generally doesn't much matter. But when you are trying to protect the control plane, it does make it a lot more difficult, because you don't actually know if the packet is going to the control plane at the filter stage. So what you would need to do is you would need to check for all the types of packets that can end up on the control plane on every interface, on every ingress filter. Well, one approach that hardware vendors might use for this is that they might put a separate filter chip or switch chip between the switch and the control plane, so that they can implement the control plane filter there. But the problem with that is that you can still end up with head of line blocking. If you've got a lot of traffic from all interfaces coming to that chip, then that chip will be overloaded, and it can't protect the control plane in all cases. Again, questions?
Hello, I'm Nikolai Konum from IT Relation, and my question for you is, have you looked into RPL language in iOS XR?
iOS XR. No, I haven't. I know there are also these P4, for example, and other languages that could also be very good alternative ways of doing the same thing I was suggesting. So, but I'll have to look at that.
Any other questions?
Well, I guess I'm out of time anyway.
Yeah.
So.
Please give a big hand to Axel.